This is part D of question 4, and this is quite a subtle question. There are quite a few nuances there and things you have to pick up and notice to get this question right. So you're given k of x, which is this graph of m times sine x. I'm going to do a sketch here to show you an example of what the graphs might look like. So we're going to have a look at m sine x, and we can rule a nice big set of axes here. So our function k of x might look something like this. This is k of x. Notice that m is a variable and it's greater than 2, so this only affects your amplitude. So these x-intercepts are fixed at pi and 2 pi. These are fixed. Whereas this q of x here is a little more tricky. Depends on the value of n, but if you think about it carefully, you're always guaranteed to have that x-intercept there. So this is an example for a particular value of n for the graph of q of x. Q of x will always have that intercept at pi. The reason is because if n's an integer, if you have sine of n times pi, if n's an integer, it doesn't matter what that integer value is. If you look on your unit circle, here's your unit circle, it doesn't matter what integer value that is, you're either here or here. So y is always 0. So no matter what value of n you have here, you're guaranteed this pi value. That's actually a really important subtlety. You could probably find that out by sketching the graphs and playing with sliders, but that's something you need to know. So these are example sketches of k of x and q of x. Okay, so it wants us to find this area enclosed in terms of m and n if n is even. Well, we need an area expression to start off with before we can do anything. So the area is equal to, and that's where that intercept is really important. It's equal to the integral from 0 to pi of this top function here is k of x, so the top minus the bottom, k of x minus q of x plus the integral from pi to 2 pi of q of x minus k of x. Now, some students might be tempted to use the symmetry argument from part A and go, oh, just chuck a 2 out there, forget about this term, and then we're right. Well, we're not, because it's not always the case that these fit into each other, that we can use that argument. It's actually only the case if n is even that works. So we can't use that argument. We have to use something like this to find the area. And once again, this is one method to go about it. You could go about it in many ways. So let's find out what that integral actually is. We want to know what that is. We'll need to define our functions first. So we can define k of x and q of x, and then it's going to make punching that in a little easier. All right, so let's define our k of x as m times sine of x. That's done, and let's define q of x equals 1 on n times sine n times x. All right, let's set up this integral, which we've written down. So it's just there. So we want the integral from 0 to pi of k of x minus q of x dx plus the integral from, remember this is just one way to go about it, 2 times pi q of x minus k of x, q of x minus k of x. What do we get? We get this expression, and this expression is going to be very useful to help us find our answer. So let's write down this area expression. We get 4m minus the cosine of 2n pi minus 2 cos n pi plus 1 all divided by n squared. Right, how does that expression help us? Well, we need to find the area enclosed by these graphs if n is even, and we need to give our answer in this form. Okay, well, here's our area function. So area equals, we're going to take that 4m minus, now cos 2n pi. I'm going to draw a bigger unit circle to show you what you need to look out for. Cos 2n pi, this term here, if n is even, if n is an even number, this is either going to be 2 pi, so it'll end up here. It could be 4 pi, so it'll end up here, 2 revolutions around. It could be 8 pi, 2, 4, 6, 8, so it'll end up here. No matter what, this quantity has to be 1 if n is even. And we can find that out by playing with the unit circle. So that quantity is 1. Let's look at the next one. 2 cos n of pi. Well, n is even, so we could have 2 pi. We could have 4 pi, which would be another term, 6 pi, 8 pi, 10 pi, so on. So it has to be 1 as well there. So that's minus 2 plus 1 over n squared. That gives us 4m minus, so 1 plus 1 is 2, minus 2 is 0, so we get 0 on n squared. Well, that simplifies simply to 4m. Now you might think, oh, but I need the answer in this form. Well, yes, this answer is in that form because b equals 0 satisfies this form because it says that a and b need to be integers. The integer b is 0, satisfies this form. So the area equals 4m, which makes sense, right? Because for the even case, I'll give you an example of the even case. It might look something like that. And the even case is that symmetrical case where this part fits into there and this part fits into there. The even case will always give you a symmetry, and that simplifies to 4m, which is quite nice. Let's have a look at the odd case. So the area equals, well, we get 4m. So we're looking at the odd case now. Cos of 2 times an odd number. 2 times an odd number is guaranteed to be even, so we have even multiples of pi. And our even multiples of pi are always going to take us back to this one value. So that's minus there, and that's always going to be 1. for the odd or even case, doesn't matter. But over here, if we had odd values of n, we could be here. We could go pi, 2 pi, 3 pi, 4 pi, 5 pi. So it's either 1 or -1 here. Notice that for the odd case, we're looking at different values here. We don't know which one. Well, let's look explicitly for the odd values. So our odd values are 1, 3, 5, 7, 9, so on. Well, 1 lot of pi gets us here. 2 lots of pi, 3 lots of pi, 4 lots of pi, 5 lots of pi, 6 lots of pi, 7 lots of pi. Aha, we've noticed something. So this is guaranteed to be -1. So that becomes +2 plus 1 on n squared. So that becomes 4m minus 4 on n squared. And yes, it is in that form because b is -4 and a is 4. I think that's one of the trickiest questions on this paper.